Bismillah ar-Rahman ar-Rahim. What is the integral from 0 to infinity of x times the hyperbolic secant of x times the natural logarithm of 1 minus the hyperbolic secant of x? Let's do a substitution. X is equal to minus the natural logarithm of t. So t is equal to e to the minus x, and dx is minus dt over t. When x is equal to 0, t is equal to 1, and when x tends to infinity, t tends to 0. The hyperbolic secant of x is 2 divided by e to the x plus e to the minus x. We want to write these two guys in terms of the new variable t. We have 2 over t plus t to the minus 1. Multiplying the numerator and denominator by t, this is equal to 2t divided by t squared plus 1. The argument of the natural logarithm becomes 1 minus 2t over t squared plus 1. This is t squared minus 2t plus 1 over t squared plus 1. This is 1 minus t squared divided by 1 plus t squared. Here is our new integral using the variable t. This logarithm can be written as 2 times len 1 minus t minus len 1 plus t squared. So our integral is minus 4 times this integral plus 2 times that integral. Both integrals have the natural logarithm of t divided by 1 plus t squared. But in this integral, we have the natural logarithm of 1 minus t. Here we have the argument is 1 plus t squared. The method that I use here to solve the problem is to investigate 4 integrals, establish relations between them, and then use these relations to get our desired result. The first integral is A. It is an integral from 0 to 1, len x over 1 plus x squared, like what we see here, but we have len of 1 minus x over 1 plus x. B is integral from 0 to 1, len x over 1 minus x squared, and then we have the inverse tangent function of x. This integral here is big C, and that integral is big D. Our target is 2c minus 4d. Before examining the relations between these integrals, let's review some useful results. If we are interested in the integral from 0 to 1 of x to the v log x to the k dx, where v and k are non-negative integers, we can solve this integral by using the change of variables x equal to e to the power z. X to the v becomes e to the zv. Log x becomes z. So this becomes z to the power k. Dx is e to the z dz. The integrand becomes z to the k times e to the power zv plus z. To have x equal 0, z should tend to minus infinity. If x is equal to 1, then z is equal to 0. Let's do another substitution. W is minus this exponent here. Now our integral will be from 0 to infinity. This becomes e to the minus w. Z to the k is minus w over v plus 1 all to the power k. dz is minus dw over v plus 1. We get minus 1 to the power k divided by v plus 1 to the power k plus 1. Integral from 0 to infinity, w to the k, e to the minus w dw. This integral is gamma of k plus 1. This is our result here. Catalan's constant is the alternating sum of the reciprocals of the squares of the odd positive integers. 1 over 1 squared minus 1 over 3 squared plus 1 over 5 squared minus 1 over 7 squared and so forth. Its numerical value is approximately 0.9159655 and so on. Is it irrational? And if so, is it transcendent? These are still open problems. We have this geometric series, summation j from 0 to infinity, z to the j, and this is equal to 1 over 1 minus z, provided that the magnitude of z is strictly less than 1. If we have minus z to the power j, then we have 1 over 1 plus z. What is the integral of len y divided by 1 plus y squared dy? The integration here is from 0 to 1. We can use this expansion here because y is between 0 and 1, and so y squared is between 0 and 1. 1 over 1 plus y squared can be written as summation j from 0 to infinity minus 1 to the j and then y squared to the power j, which is y to the power 2j. We can integrate this power series term by term. We have summation j from 0 to infinity minus 1 to the j, and then we have this integral. This integral is like our friend here. This log is the natural logarithm. K is equal to 1 because the logarithm is raised to the power 1, and v is equal to 2j. So this integral is minus 1 to the power 1, that's minus 1. Gamma of 2 is 1 factorial, so that's 1. And then we have 2j plus 1, all raised to the power k plus 1, which is 2. This integral is minus 1 divided by 2j plus 1 squared. It is this alternating sum of the reciprocals of the squares of the odd positive integers. Because of this minus 1, what we have here is minus Catalan's constant. What if we have the same integration, but in the denominator we have 1 minus y squared? In this case, if we do the series expansion, we will not have this minus 1 to the j. We just have y to the power 2j. We have similar steps, but here we will not have minus 1 to the power j. We have minus, between brackets, the sum of the reciprocals of the squares of the odd positive integers. These guys are equal to the sum of the reciprocals of the squares. But then we need to subtract 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared and so forth. From this bracket, we can take 1/4 as a common factor. This summation here, that's zeta of 2, which is pi squared over 6. And here, this will be 1/4 of zeta of 2. This summation here is minus pi squared over 6, between brackets 1 minus 1/4. Thus, this summation and that integral both are equal to minus pi squared over 8. Let's establish now our first relation. We will establish our relations mainly using integration by parts. So I will write down this integral as integral from 0 to 1, this logarithm, d, and then I will put here minus the integral from x to 1, the natural logarithm of y divided by 1 plus y squared dy. Let's recall how we do differentiation under the integral sign. If we have an integral from alpha of x to beta of x, these are two differentiable functions in x, and then we have omega of x, y, dy. We want to differentiate this with respect to x. We have three terms. The first term is an integral in which the integrand is the partial derivative with respect to x. Then we have another term, which is the derivative of beta with respect to x. Then we take the integrand and replace the dummy variable of integration by the upper limit. So that's omega of x, y is changed to beta of x. We have a similar term involving the lower limit of integration, but with a minus sign. And of course, the dummy variable of integration y is replaced by alpha of x. If we apply this rule here, x is not in the integrand, the upper limit of integration is a constant. So what we have is minus, this minus here, then another minus dx by dx, then ln x over 1 plus x squared. This is 1. We get this part here. Now we carry out the integration by parts. We will have an integral from 0 to 1, then this integral here from x to 1 ln y over 1 plus y squared dy. And then we need to differentiate this function of x. And when we do so, we get minus 2 over 1 minus x squared dx. We also have the product of these functions of x. And we need to take the limit as x tends to 0 from above and as x tends to 1 from below. When x tends to 0, this integral becomes the integral from 0 to 1 ln y over 1 plus y squared. That's minus g, as we have obtained on the previous page. But this logarithm will be the logarithm of 1, which is 0. This limit is equal to 0. What about this one? There is no problem in ln 1 plus x. The problem is when x tends to 1 in ln 1 minus x, the argument tends to 0 and the natural logarithm tends to minus infinity. And ln 1 minus x is multiplied by this integral. When x tends to 1, the measure or the length of the domain of integration tends to 0 and the integral tends to 0. So we have something tending to minus infinity multiplied by something approaching 0. So what is the limit as x tends to 1 from below of minus ln 1 minus x? With this minus sign, the numerator tends to infinity as x tends to 1. And then I will take this integral and make it downstairs in the denominator. So this tends to 0 and this ratio tends to infinity. We are in an infinity over infinity situation. We can resolve it by applying L'Hopital's rule, which tells us that this limit can be obtained via the limit of the ratio of the first derivatives. The derivative of the numerator is 1 over 1 minus x. The derivative of the denominator is minus 1 over the square of the integral. Then by the chain rule, we need to differentiate the integral itself. We will have another minus 1 because x here is a lower limit of integration. Then we have ln x over 1 plus x squared. This 1 plus x squared tends to 2 as x tends to 1. After rearranging the terms, we get this. The integral now is in the numerator and it is squared. So we have something approaching 0 as x tends to 1. In the denominator, we have the natural logarithm of x and then 1 minus x. Both terms tend to 0 as x tends to 1. We are in a 0 over 0 situation and we need to apply L'Hopital's rule again. We get this ratio. This term here tends to 2 as x tends to 1. We end up with the integral times ln x in the numerator. In the denominator, we have 1 over x minus 1 minus ln x. And this also tends to 0 as x tends to 1 from below. For a third time, we will apply L'Hopital's rule. And after this third application, we will get this quantity in the denominator. If x tends to 1, this tends to minus 2. So finally, we don't have 0 in the denominator, and we can check that the numerator tends to 0. So the limit is equal to 0. The only survivor is this integral here. I will write the integral with respect to y as an integral from 0 to 1 minus an integral from 0 to x. The integral from 0 to 1 is minus g. The integral a now looks like this. In this inner integral, we do the substitution. Y is equal to xt. When y is equal to 0, t is equal to 0. When y is equal to x, t is equal to 1. This y becomes the product xt. The numerator becomes ln x plus ln t. dy is equal to x dt. We can separate this integral into an integral that contains ln x, which can be taken outside because the variable of integration is t. Then there is another integral from 0 to 1, 2x over 1 minus x squared, ln t divided by 1 plus x squared t squared dt. We can write down this product as 1 over 1 plus t squared, 1 over 1 minus x squared plus t squared over 1 plus x squared t squared. This part here will give us an integral from 0 to 1 ln t over 1 plus t squared. That's minus g. When we integrate with respect to t, we have 2g over 1 minus x squared. And from here we have minus g times 2x over 1 minus x squared. So we have 2g, an integral from 0 to 1, 1 minus x over 1 minus x squared. This is 1 over 1 plus x. The integral is the natural logarithm of 1 plus x. Evaluated at 0, this is 0. Evaluated at 1, this is the natural logarithm of 2. So part of our result is 2 times the natural logarithm of 2 times Catalan's constant, g. We have this integral. If we do the integration with respect to t, we get the inverse tangent function of xt divided by x. This x will eliminate that x. We are left with 2, the natural logarithm of x divided by 1 minus x squared. When we use our limits of integration, the inverse tangent of 0 is 0. The inverse tangent of xt when t is equal to 1 is the inverse tangent of x. We have one last integral in this part. We swap the order of integration because it is straightforward to integrate with respect to x to obtain the natural logarithm of 1 plus x squared t squared. After using the limits of integration, we get the natural logarithm of 1 plus t squared. Here are our four friends. We have a equal to 2g ln 2, and then we have double this integral, which is b. Then we have this integral, which is c. It is clear that we still have more work to do, as this relation alone will not help us obtain our original integral, which is 2c minus 4d. Let's start with a again. We will also do integration by parts, but this time we will write a as integral from 0 to 1. Then we have the logarithms. Then d tan inverse x. The integral that we get from here is minus integral from 0 to 1 tan inverse x. Then we need to differentiate this product. Then we have the limits. Both limits are also equal to 0 in this case here, and both can be obtained using L'Hopital's rule. We can split this integral into two integrals. 2 times the integral from 0 to 1 logarithm of x times the inverse tangent of x over 1 minus x squared. That's b. We have this other integral. We do a change of variables, x equal to 1 minus y over 1 plus y, which means that y is 1 minus x over 1 plus x. We get minus 2 integral from 0 to 1, 1 plus y over 1 minus y, ln y over 1 plus y, all squared. Then this tan inverse x becomes tan inverse 1 minus y over 1 plus y. Tan inverse alpha minus tan inverse beta is tan inverse alpha minus beta over 1 plus alpha beta. Let's apply this here. We have tan inverse 1 minus y divided by 1 plus 1 times y. By this rule, this function can be written as tan inverse 1 minus tan inverse y, and tan inverse 1 is pi over 4. This integral is split into two integrals. In one of them, we have 2, and then we have tan inverse. We have the natural logarithm. We have 1 minus y squared in the denominator. So we have 2 times b. Together with 2b from here, we end up with 4b. Then we have minus pi over 2, integral from 0 to 1, ln y over 1 minus y squared dy. We have done this integral on the first page, and it is equal to minus pi squared over 8. This product is pi cubed over 16. This may seem like it is going forever, but we will have a third relation, and with that third relation, we would be able to obtain the value of our integral. This is our third and final relation. Now we start with the second guy, this integral. Again, we do integration by parts. We write b as the integral from 0 to 1 tan inverse x d, and then we put here the integral from 0 to x ln y over 1 minus y squared dy. Applying the rule for differentiation under the integral sign, this will give us the natural logarithm of x divided by 1 minus x squared. We get the integral from 0 to 1, then integral from 0 to x ln y over 1 minus y squared dy. We need to differentiate this guy. That's 1 over 1 plus x squared. Then we have limits to take. If x tends to 0 from above, the length of the domain of integration shrinks to 0, and tan inverse 0 is 0. So this is definitely 0. When x tends to 1 from below, tan inverse x tends to pi over 4, and this integral approaches the integral from 0 to 1 of ln y over 1 minus y squared dy. This is minus pi squared over 8. So the limit here, as x tends to 1 from below, is minus pi cubed divided by 32. Let's do the substitution, y equal to xt here. When y is 0, t is 0. When y is x, t is equal to 1. Ln y becomes ln x plus ln t. And dy is x dt. We can separate this ln x here. Then we will have the integral minus from 0 to 1 x ln t over 1 plus x squared, 1 minus x squared t squared. We do partial fractions. 1 over this product here can be written as 1 over 1 plus t squared, between brackets 1 over 1 plus x squared plus t squared over 1 minus t squared x squared. We have three integrals. This one, we can separate the variables. The integral with respect to t gives minus g, and the integral with respect to x is 1/2 the natural logarithm of 1 plus x squared. This is 0 when x is 0, and this is 1/2 ln 2 when x approaches 1. From this limit, we have minus pi cubed over 32 from this integral. And because there is a minus sign here, we have 1/2 g, the natural logarithm of 2. Then we have this integral and that one. The trick is to rename x as t and t as x in this integral, then swap the order of integration. This integral is from 0 to 1, from 0 to 1, t ln x, x squared over 1 plus x squared, then 1 minus x squared t squared, dx dt. Interchanging the order of integration, we get this integral here, which can be combined with this integral. We have x ln x here and there. We have the same denominator. Then we have 1 from here and xt from there. In the denominator, we have 1 minus x squared t squared, which can be factored as 1 minus xt times 1 plus xt. This and that go away. The only remaining term that contains the variable of integration t is 1 minus xt in the denominator. This integral is minus ln 1 minus xt divided by x. This x goes with that x. When t is 0, this is 0. When t is 1, we have the natural logarithm of 1 minus x. Who is this guy? It is the integral d. These are the relations that we have obtained, and this is the target. 2c minus 4d. We have c here, and we have d there. Seems like a good idea to multiply this by 2. Multiply this expression by minus 4. When we add, we get 2a minus 4b. On the other side, we have the target, 2c minus 4d. Then we have 2g ln 2 plus 4b plus pi cubed over 8. Let's move these three terms to the left-hand side. We have 2c minus 4d equal to 2a minus 8b minus pi cubed over 8 minus 2g ln 2. Now it's time to employ the middle expression. It has a and 4b here. So this is a minus 4b equal to pi cubed over 16. Here we have 2a minus 8b. This is 2 times pi cubed over 16. That's pi cubed over 8. And this goes away with that. We are done. Our integral of interest, which is 2c minus 4d, is minus 2 times the natural logarithm of 2 times Catalan's constant g.